So to get a sense of how I'm going to plan to use these identities, let's take a look at this opening question here in the general idea. So how could I use one of the above identities, either from this red group or this blue group, to try to evaluate this cosine cubed integral that I'm looking at here? Now, it's really important to note that we have to be very careful when we come across questions like the one listed here, because there are some very, very common wrong answers. Here's a very common wrong answer that I see all the time. I see a lot of students going, okay, Kyle, this is pretty easy. Can't I just easily go, this is cosine, to the fourth power, and then I just divide by a fourth out front. Oh, and even easier, don't forget, boom, plus c, not going to trick me. Well, notice that this is definitely wrong, and I could double check that this is wrong by simply taking a derivative. Notice if I took a derivative here, the fourth power does come down and cancel the quarter, and then I'd be left with cosine to the third, but then I would have to perform a chain rule, and I would get something like cosine to the third of x times a negative sine of x. And this is certainly not what I started with, and so this is certainly not the right answer. So I have to be very careful when interpreting what I have here, that I can't just do a power rule in reverse. So when I think about all of the different integration techniques that we discussed, I can see that this isn't a derivative rule that I know from Calc 1. I don't really know how to do much algebra with this. A U substitution is going to be hard. Integration by parts would probably be really messy, but a trig identity could be useful. I'm actually going to go ahead and make use of this red identity right up here at the top. And I'm going to mark that this question here is being completed with a red identity. So here's what I'm going to go ahead and do. I'll start by saying we see that the integral for a cosine cubed could be re-expressed as a cosine squared of x times a cosine of x. Right? I'm just kind of separating that third power out into a power of 2 and a power of 1. Now there's a reason that we're going to do this. What we'll see is that when I use identities from the red group, my goal is often going to be to use an identity to allow myself to eventually do a U substitution. So I'm making this separation planning on using this green portion over here as du in a u sub. That is, I want the derivative of my u to be cosine x dx. Now that might lead you to see that, well, that would mean that u would have to be sine of x, so the derivative would be cosine of x. But I don't have any signs in my integral right now that I can go ahead and replace. However, if I make use of the red identity that I have listed up here, I can easily state that the cosine squared is equivalent to 1 minus a sine squared, right? That's easily seen by just taking my sine squared of x and subtracting it to the other side. Notice that everything else in the integral stays exactly the same, but I have something now with signs in it, and so I'm ready to make a u substitution. So I'll say we now do a u sub. So I'll let u be equal to a sine of x. Du is then equal to a cosine of x dx. So this seems like something that I can now go ahead and easily replace. Let me go ahead and continue the problem down here. I should now have something like a 1 minus a u squared. Notice if I had a sine squared, and sine and u are the same, I should now have a u squared. All of this stuff at the back just gets replaced with a du, and now that's a very easy integral to work with. I can see that this is going to produce u minus a 1/3 u cubed, don't forget, plus c. Now remember, since this is an indefinite integral with a u substitution, I'm not quite done yet. I would have to go ahead and substitute back in whatever u is. And since the u is the sine of x, if I was to go ahead and replace this, I would be left with the following result. So here's a good answer for what is an antiderivative of a cosine cubed of x. And I can see here that I used a red identity to help me perform a U-sub. And that's really going to be the trick or the key that's going to be taking place anytime I use one of these red identities. Now, if we take a look down at example 1, we'll see that there's another type of way that I might be able to use trig identities here. Well, let's take a look really quickly at this question. I want to find the area under a cosine squared of x graph from 0 to pi over 4. Okay, if this is the case, then let's see, an antiderivative for cosine squared of x. Well, that's not a derivative rule that I memorized in Calc 1. I don't know much algebra. U sub by itself seems hard. Not quite sure how to do integration by parts with this. We could try an identity. But notice, I can't really start by creating a green something that I'll end up using as a du. Because notice if I try to separate this out into a cosine and a cosine, right, that would leave me with something like a cosine of x, another cosine of x, and a dx. And if I attempted to save this as a du, then I'd have to come up with something over here to replace cosine with. But if I take a look at what I have up above, I don't have any identities that really can help me very easily just get cosine of x equals. At least, it seems very difficult to do that without introducing a whole bunch of square roots or other squared terms that are going to make the rest of the integration a lot harder. So instead, when I have this value squared, I'm going to notice, wait a minute, cosine squared already exists in so many of these identities. I could use a red identity and say cosine squared is equal to 1 minus sine squared, but then notice that I'm going to have to integrate something with sine squared in it, and that has the same complexity or difficulty in integrating that regular cosine squared did. So instead, it's in this moment when I have a cosine squared or a sine squared that it can be really advantageous to use one of my blue identities. Notice here, my cosine squared of x can be equal to some quantity here that has only cosine to the first power, which is going to make it much, much easier to integrate. So I'm going to go ahead here and mark this with blue to indicate that I'm using one of those blue identities. Let's see what we have. Well, start by saying that this integral could be replaced by my 1/2 1 plus cosine of 2x. This should actually be much easier to integrate. Notice, I'm going to go ahead and I'm just going to leave the 1/2 on the outside of the integral, and I'll just do the antiderivative of everything else. Antiderivative of 1 is super easy, that's just x. And actually doing the antiderivative of a cosine of 2x can be done in multiple ways. You might be able to use a u substitution to finish it, which requires a lot of extra work and changing your bounds and a whole bunch of other stuff, or you can almost kind of eyeball this. This is the way that I would think through it. A cosine would have to come from a sine in the antiderivative. But of course I could check my work right now to see if this will be sufficient. Before I evaluate, let's just quickly double check. Obviously if I take the derivative of x, I get 1. But if I take the derivative of sine 2x, I'm going to get cosine of 2x, but then I'm going to have to chain rule and do it times 2. To catch that times 2 and stop it from appearing in the front, I can just kind of front load this with a 1/2. Now notice that when that times 2 pops out, it's going to cancel out with the 1/2, and I'll just be left with a cosine of 2x. Notice then that's a very, very simple and quick way to try to go ahead and find that antiderivative. Okay, so now that I'm here, I can easily go ahead and start my evaluating. So let's see, I'm going to have a 1/2 times a pi over 4 plus a 1/2 times, let's see, if I double pi over 4, I'm going to get pi over 2. And then if I plug in 0, let's see, 0 plus a 1/2 times the sine of 0. Well, if I look at that, everything over here at the back is pretty much just 0, right? Sine of 0 is 0, and so all of this is just nothing. Now sine of pi over 2, that's a 1, so really this is just 1/2 times the quantity pi over 4 plus a half. And so I can go ahead and if I wanted to, I could distribute that 1/2 that I have out front and make that pi over 8 plus a quarter. And I have a final answer. So in the event where I have these individual sine or cosine values that are being squared, it becomes very easy to see that a blue identity could be useful. And again, when I have it maybe not squared, but where I could possibly peel off some extra terms, I might be able to set up and force a U substitution. This is going to be kind of the general theme throughout the section, and in all the remaining videos we're just going to try to take a look at some different ways that we can recognize some patterns that are kind of similar in style to these two techniques that we've seen here.